It's a real pleasure to be here today and able to talk not just to the people who know something about superconductors, some of whom are in the audience. So forgive me, we're not going to talk in very much detail at the same level as we were earlier in the meeting, because my aim today is to talk to the people who don't know so much about superconductors and to give you a flavour for what we might be able to do with them in the future. So the title, Can Superconductors Help to Save the Planet, is a little bit provocative, I guess, and I'm not going to be able to answer it completely, of course, but where I'm going to start is what everybody's very familiar with at the moment, and that is that we're in a climate crisis. You know, global warming is causing all of these sort of natural disasters to happen, more flooding, more wildfires, sea rises, sea levels rising, and these are all reports from the last month. Which have been attributed in part to global warming. So just in the last month in the news. So a lot of the problem with climate change, I guess, is that we're producing greenhouse gases, and we're doing that by burning fuel, fossil fuels mainly, coal and gas and oil. And that's creating gases that are then warming up the planet. So everybody's very aware of this. It's been in the news an awful lot. But if we look at what's going on in terms of the energy demand, starting back in '95, we're here for the global energy demand. And you can see it's just rising and rising. We're now somewhere here, and the expected energy that we're going to need is just keeping on going up. If you look at the colours on the bars, you'll see that the bottom two, the dark blue and grey, are coal and gas. So they're the fossil fuels that when we burn them, we release carbon dioxide and other greenhouse gases. The brighter blue and green and yellow at the top are the renewable energies, which everybody knows is more environmentally friendly. And as you can see now, globally, we're still reliant on the fossil fuels mainly. And the idea is that by 2050, we'll increase the output of renewables so that we can bring down fossil fuel consumption. But you'll notice that even in these predictions, we're still going to be needing quite a lot of fossil fuels to burning those to make our energy, even with the big expansion in renewable energy. There's this bar in the middle, which is nuclear. And I mention this because obviously in the UK, we have some nuclear. About 17% at the moment of our electricity comes from nuclear power. And it's one of the ways that we might be able to make a difference if we increase this. And also there are new nuclear technologies, which I'm going to talk about, different kinds of technologies that can also help here. So if we have a look at what happens with our energy at the moment, this is sort of UK focused. We've got mainly fossil fuels, coal, oil, that kind of thing. In fact, we don't use very much coal in the UK anymore. We have renewables, which are mainly wind power, and we have some nuclear. That gets generated, we generate electricity, and it gets transferred across the countryside on overhead power lines mainly to where we need it. I put houses and factories, but obviously there's lots of places that need it. In addition to that, we obviously burn gas mainly to heat our homes, and transport. A lot of our transport is still done by fossil fuels, petrol and kerosene and diesel and things like that. So if we have a look, first of all, at transport, about 12% in the UK of the greenhouse gas emissions come from transport. So one of the things that people want to do is to move, and about 80% of the houses are heated by gas. So we're still using these sort of not electrical sources for heating and for transport. One of the things that what people want to do is to switch to electric, to be more green. And we can do that with electric trains. In the UK, we've got lots of electric trains, actually, but around the world, there are fewer. Electric cars, obviously, are a big thing. They'll be draining resources on the grid. So we'll be needing electricity from the grid to power those cars, to charge those batteries. Aircraft, they had a talk earlier in this meeting about electric aircraft. And this is part of the drive towards reducing the carbon emissions from aircraft by 2050 to be net zero by 2050, and maybe using new fuel supplies like hydrogen to do it, also in ships. So a switch to electric. But that's not going to be very good if we're still generating our electricity that we're feeding it with by coal and gas. So if we're increasing the amount of electricity we need, but we're not generating more, then we're going to be in a problem. So what we really want to do is to get rid of the greenhouse gases from burning fossil fuels to make electricity, 12% in the UK. Remove that by putting more renewable energy, offshore wind mainly, and we're probably going to have to build more nuclear power stations as well to try to help with that. And looking further in the future, new technologies for generating clean electricity. And one that I'm going to talk about today a bit later on is nuclear fusion, which isn't done commercially yet, although experimentally it's been done. We haven't made any energy out of it yet, but this is the kind of power that's used to power the sun. So it's how we can harness that on Earth. So coupled with switching to electric, we need greener energy generation or electricity generation. Also coupled with going to renewables, the supply is more disturbed. It's not so constant as it is with burning coal and gas. So we need to store that energy to smooth out the power supply. So we're going to need new technologies for doing that. If we're talking about usage of electricity, so one of the other ways we can save ourselves some of this energy is to reduce our usage. So we could make things more efficient. So at the moment, most of our electricity actually goes to powering motors, rotating machines of some sort or another. In factories, in homes, air conditioning, fans, all those kinds of things, all use electricity to generate mechanical energy. The other thing that might interest you is that in the distribution of electricity from one place to another around the countryside, we lose about 8% of all the electricity we generate just in getting it from one place to another. So we want to improve efficiencies as well. So the question is, how can superconductors help us? And to answer that, we first of all want to talk about what a superconductor is. So superconductors, not surprisingly, are materials that conduct electricity really well. They're very good conductors. But to understand what we mean by that, it's a good idea to have a look at what happens in a normal metal, which is a pretty good conductor of electricity. What you have are the electricity is carried by electrons, and electrons start off being tied to atoms, but in a metal they separate. Some of the electrons separate from the metals. So you end up with these atoms here, and the electrons bobbing around in between them, free to move. And if we connect our metal up to a power supply, like a battery or something, then the electrons will want to drift from the negative side, the negative terminal, towards the positive terminal. Okay, and we call them free electrons, but they're not quite free because they're going to hit things. They're going to hit those atoms as they move. And when they hit them, they get scattered, they get knocked off course, and they lose some of their energy when they do it and generate heat. And that's what we call resistance. And if we didn't have any resistance, then we wouldn't need the battery to keep those electrons moving. But because they hit things and get knocked off course, then we have to keep the battery there to keep pushing the electrons through the material. So one of the other things that's worth noticing is that this is a very schematic picture, and these atoms that are in a nice array there actually will be moving around. They'll be jiggling around all over the place. Well, they'll keep close to where they are, but they'll be moving around. And as they get hotter, they move around more, and they are more likely to knock those electrons off course. So the resistance increases when you increase temperature. So this is what this graph is showing, that the resistance increases when we increase the temperature in a metal. Now, back in the early 1900s, there was lots of debate on what would happen if we cooled those materials down, lower and lower temperatures. And there were some people who thought that it would just keep going down like this until it hits zero. So at zero temperature, absolute zero, we'd get zero resistance. Other people thought that it would level out and we'd always have some sort of resistance, even if we got down to the lowest possible temperature. And some people even thought it would increase like this as we got to very low temperature. And nobody knew, because they couldn't get cold enough temperatures, until this man here in his lab, Kamerlingh Onnes, in 1911, managed to liquefy helium, which has a boiling point of 4 kelvins, that's 4 degrees above absolute zero. And then he could do experiments on metals at very low temperature. and he measured mercury was the first material he used because he could make it very pure. The other person in this picture, I think, is van der Waals. So if there's anybody who's been doing chemistry or physics A-level, you might have heard of van der Waals. So what did he find when he cooled down mercury to these very low temperatures? Well, it surprised him because he found that the resistance of the mercury suddenly dropped from this value here to absolutely nothing when he got to very near his lowest point, 4 Kelvin. And what's more, if he heated it up a bit, it would go back and the resistance would come back again, and he could do this repeatedly. And this really is zero resistance. It's to all intents and purposes, it's absolutely nothing, this resistance here. So, and we call this the critical temperature, the temperature below which it becomes superconducting, and it has no resistance at all. And what that means is that electricity can flow with there not being any friction, essentially. If you push a shopping trolley across the floor, eventually it will stop because of the friction of the wheels. And the same happens if you turn off the power supply in a metal, the resistance will stop those electrons flowing. But in a superconductor, if you've got the electrons moving, you can take the power supply away and they'll keep going all by themselves without the power supply anymore. So what does that mean? So superconductors have zero resistance. That means that we don't generate any heat. There's no resistance, and it's the resistance that generates the heat. It's the scattering of these electrons off the atoms that generates the heat. So what does that mean? It means it's more energy efficient, so we can transport our electricity around the place without generating all this heat and losing the energy. And also, not maybe so obviously, it means that we can carry larger currents through the same amount of wire, the same cross-section of wire. And the reason for that is that in a normal metal, if we start increasing the current through it, it starts generating heat. That heat increases the resistance of the metal, which generates more heat, and eventually it's going to melt. So there's some limit to how much current we can get through it without it melting. And superconductors do have a limit as well, but it's a lot higher. So this piece of wire, if it was copper, it's got a cross-section of about 1 millimeter squared. If it's just copper, it will carry about 20 amps, maybe 10 to 20 amps. But this is actually a piece of niobium titanium superconductor. So at 4 Kelvin, it will carry probably near 1,000 amps. And that's what superconductors are really good for, carrying really high currents in really small spaces. Of course, there's the caveat that we've got to go down to low temperature to make them work. So if we could do this all at room temperature, then I think they'd be everywhere. And they would have been a long time ago. But we can only do them at very low temperature. So it's a very interesting phenomenon that nobody had come across until the 1900s, the early 1900s. But you would think maybe that it's very special and only a very few materials show superconductivity, but that's not true at all. So here's a periodic table, and if we just look at all the elements in here, all of the ones that aren't grey superconduct. Some of them better than others. So all the ones in dark green are the best ones. They superconduct above liquid helium temperature, which is 4 Kelvin. The ones in orange need some pressure applied to them to superconduct. But pretty much the whole periodic table is superconducting. And this is only the elements. So if we talk about alloys and compounds, then pretty much everything here is in one or other superconducting compound. Okay, so it's not limited to particular areas of the periodic table or particular types of material even. So this is the standard graph that's shown when you're talking about the history of superconductivity. So on the y-axis here is the transition temperature. So this is the temperature below which you've got to cool it for it to be superconducting. And this is the year of discovery. Now there's only a few dots on here, but there are actually thousands and thousands of superconductors, and I've only put a few of them on, and I haven't labeled very many of them either. So the first one down here was mercury, and all these first ones would be elemental superconductors. But quite soon after that, they realized that they didn't need to be elements at all. They could mix them together and make alloys and create better superconductors, so ones with higher critical temperatures. So niobium tin and niobium titanium, this one and this one, these are rather special superconductors because they're ones we can go and buy in the form of wires. So they're here on the left-hand side, niobium titanium and niobium 3 tin. So you can go and buy those commercially. During the 1900s, the temperature gradually crept up There were some other families that were discovered, completely different kinds of superconductors that were discovered. But in the highest one of this series that we found so far was discovered in 2001, so really quite recently, and that's magnesium diboride, so a simple binary compound will superconduct at about 40 Kelvin, so it's pretty good. Now, this is all interesting, but we need to cool these down to temperatures that are pretty low. 40 Kelvin was about the highest. And so nearly everything was using liquid helium, which is an expensive coolant. It costs about the same as whiskey, I'm told. So it's quite expensive. However, in the late 1980s, a new discovery was made that was very surprising because nobody thought you'd be able to get superconductivity at such a high temperature. But a whole new family of compounds, which we now call the high temperature superconductors, which are based on copper and oxygen, so they're oxides. These were discovered, and they've got critical temperatures much higher and importantly above the boiling point of liquid nitrogen, which is 77 Kelvin. And liquid nitrogen is much cheaper and easier to cool. So as a cryogen, it's much more viable for lots of commercial applications. So these have got very complicated names, and again, I've only labeled a few of them. IBCO or YBCO, that's yttrium barium copper oxide. This one, BISCO, is bismuth strontium calcium copper oxide. And the numbers here refer to how many of each of the elements you've got in the compound. So there are two different BISCO compounds, 2223 and 2212, which you can both go and buy as commercial tapes. So you can see them over here. They're part of our technological superconductor family. IBCO or REBCO more generally, you can replace the yttrium with other rare earth elements. You can buy that as well in the form of a tape. And I'm going to talk pretty much exclusively today about this material, which is this YBCO tape called cotoconductor. So why might these high temperature superconductors be useful? So I'm going back to our sort of picture of what we've got at the moment. I mentioned that about 8% of electricity is lost in the transmission lines. So the most obvious application of superconductors probably is the fact that because they've got no resistance, we could transport our electricity across the countryside without wasting that 8% of electricity. We'd have to cool them, which is a problem, but potentially we could save some energy there that's lost at the moment. And the prediction, this is Furukawa's prediction, is that they can reduce the energy loss by 77%. Now, I wouldn't like to stand up and say that that's always the case, and it probably depends on which particular kind of cable we're talking about. But it is possible. There are predictions that we can save the energy even with the cooling that we need by quite some margin. The other thing that's good about them is that actually they're quite relatively easy to engineer. So the material itself is not easy to engineer, and we'll come back to that, but the cables are quite simple. So all you need is because it's liquid nitrogen cooled, all you need is a conduit down the middle to have the nitrogen flowing through it, and probably a return around the outside for the nitrogen to go through. And then you can make a cable. It's not that different from a cable that transports liquid natural gas, which is done already. So relatively easy to engineer. And then, as I mentioned before, we can get a lot more current down the same amount of material. So we can get about 150 to 100 times as much current to the same cross section, which means that here, this is a demonstrator that was built at Long Island some time ago now, and these are the superconducting cables, and they carry as much power as all of those overhead ones do. So you can get the same amount of electricity in a much smaller space. And that might be beneficial in places like Tokyo, which are very difficult to get new power cables and underground power cables. You could replace your underground cable, conventional cable, with a superconducting one, which carries much more current. So this idea of superconductors carrying a lot of current in a very small space is useful for magnets. And magnets may not seem like a terribly important thing, but actually in the energy sector, magnets come in everywhere, as we'll see in a minute. So to generate a magnetic field, yes, you can take a piece of magnet, a piece of iron or something like that that is magnetic. But nearly always what we do is we take a loop of wire something a bit like this, a coil of wire, and we pass a current through it. And the bigger the current we pass through it, the more magnetic field we generate in the middle of that coil. We can also make more magnetic field by winding the magnet round more times, winding the wire around more times in the same space to get more turns of the magnet. Both of those will increase the magnetic field inside. So superconductors are great because we can get lots of current down a very little bit of wire, so we can get lots of turns carrying lots of current, so we can make very big magnetic fields. This is a let's go back. This is a conventional magnet. I think it's about a 10 Tesla magnet made without superconductors. It's a big thing. Probably takes about the power of a small city to keep that going. Whereas this is a 10 Tesla magnet, which is in one of our labs in Oxford. And that probably takes a couple of kettles or so to keep that going if we keep the field the same. So they're much more efficient. We can get stronger magnetic fields and we can make them more compact because of this, this amount of current we can get into the very small diameter of wire. So that's why superconductors are really good for magnets, and that's where they've really come into their own. So there's quite a history of superconducting magnets in Oxford. So just down the road from here at the Clarendon Laboratory, which is part of physics department, there was lots of work all the way through actually, but in the 1950s, somebody called Nicholas Curti was working on getting very low temperatures. In fact, he was trying to get, he managed to get microkelvin temperatures. So if we're talking about microkelvin, that's 1/1000th of 1 Kelvin. And 1 Kelvin is the same unit as a degree. It's the same sort of spacing as a degree. So he was working on very, very low temperatures and managed to get this, these microkelvin temperatures, which were the coldest spot on Earth at the time. So he got a world record for that at the time. And he had a student, Martin Wood, who set up a company. It was the first sort of spin-out company of the university to make magnets. And he realized quite soon after he did this in 1959 that actually superconducting magnets were the way to go. And so he started making commercial superconducting magnets, and this is one of them here, one of the first ones. And here he is testing it in the Clarendon labs. And he made them in his shed, in his garden shed. So it was the world's first spin-out company from a university. And Oxford Instruments is still going strong in Oxford, obviously, and has expanded into lots of different areas as well. But they still make magnets. And there are other places in Oxford who are making magnets. So Siemens is one of them. And what they realized quite soon after making these magnets was that one of the first commercial applications of them, in fact, the main commercial application still, was in magnetic resonance imaging machines. So if you've ever been and had a body scan to diagnose problems with your joints or something like that, you're wheeled into a big magnet like this. This is the superconducting magnet. And they're made out of niobium titanium, most of them, which is our favorite superconductor, one of our original low temperature superconductors. And they're operated in a very interesting way because you can make a completely closed circuit with this coil. If you close it with something that superconducts, you can make a completely superconducting circuit. And then what happens is that when they install it in the hospital, they take it in, they have a special switch, they can open that and connect it to the power supply. They can start the current going, they can close the superconducting switch and take the power supply away. And then it stays superconducting for preferably its lifetime, unless somebody presses the big red button and turns it off for safety reasons, then they have to come back with the power supply. But they essentially just leave it operating like a permanent magnet with no power supply at all. And the good thing about that is it means that the magnetic field is really stable. It doesn't change because with the power supply, you get fluctuations with the voltage and things like that. And here we're operating without a power supply. It just stays very, very stable with a decay time of about 10,000 years if you get the resistance of the joints low enough. It's something that we've been looking at in Oxford in terms of research in the last few years, because although these joints can be made commercially by Siemens and Oxford Instruments and lots of other people, it's a bit of a proprietary secret how they do it, but they can be made and done very reliably. They use lead-based solders usually for doing it, or that's one of the ways it's done. And lead is something that everybody's trying to get rid of in industry. And they have an exemption at the moment for MRI to use lead still. but they're very keen to get solders that don't include lead, or other ways of joining these magnets that don't include lead but are still superconducting. So in Oxford, we've been working on new solders. This is an indium tin bismuth solder, nowhere near as good as lead bismuth, unfortunately. We've looked at things like spot welding, and there's been quite a lot of work going on that, I think. And the other thing that's interesting is that we're going to talk about high temperature superconductors, and there isn't the same technology available yet for joining high temperature superconductors. So although we can join low temperature superconductors, we can't join the high temperature superconductors. So if we now come back to our picture of how superconductors might help us here, we've talked about transmission wires, but the next thing to think about are motors and generators. So again, you may not think about this very much, but motors and generators, so motors are things that obviously make things rotate. You put electricity in and you make things rotate. Generators do the opposite. You start with something rotating like a wind turbine and you generate electricity from it. They're essentially the same device. And they've got usually some sort of permanent magnet on the outside and then some coils that rotate on the inside. And we can think about replacing those with superconductors instead. And the kinds of advantages we might get, for wind generation, we might be able to make them smaller and cheaper. So wind power, to get more and more power from these wind generators, like the offshore wind generators, they have to go to bigger and bigger turbine blades, 50 meters plus. That's the only way they can get more power out of them. But places like companies like GE are looking at using, in fact, persistent mode technology, a bit like the MRI, to do this with much smaller and cheaper ways using superconductors. So much smaller systems, which will be cheaper. Aircraft. So here, it's really important that you've got good power to weight ratio for your motors and any generators that you want for electricity in aeroplanes. And it's not really, certainly for long haul flights, it's not really going to be possible to achieve the power to weight ratio that we need just using conventional electrical techniques at the moment, machines at the moment. So people like Airbus, and we heard from GKN earlier, are really seriously looking at using superconductors in for the magnets and for the motors and generators, and possibly some transmission in these aircraft of the future. So the kind of aircraft that we hope to have by 2050. So there's also some superconducting demonstrator magnets for ship propulsion. That says 3.6 megawatts, but I think it should be 36 megawatts. It's quite a big machine. And again, it's using superconducting technology, and that was a US Navy project with one of the companies that makes the tape. Possibly more efficient motors for powering devices, possibly with some sort of low friction bearings, which I'll talk about later. Another technology that we need is this energy storage, which when we go into more renewables, we're going to need that. Superconductors can help us there as well, because if you've got a superconducting circuit, you can dump energy into it and keep it there, and it doesn't lose any energy for the time that it's there, and then you can recover it again when you need it. So it's a good temporary store of electricity, and it's one of the most efficient stores that you can think of, and it can be charged and discharged repeatedly and quickly. So it's quite good for that. The application I'm going to talk about for a few more minutes now is fusion. So I said that that one of the things we might want to do to increase our or decrease our reliance on coal and gas in the long term is to have new technologies, and fusion is one of the ones that's being worked on all over the place, but in Oxfordshire particularly. And this is a picture of the big fusion reactor ITER that's being built in the south of France at the moment. So why is fusion a good idea? But if we look here on this graph of energy density for different fuels, so if we look at it on the volume, so energy per unit volume on this axis and energy per unit weight on this axis, we can see that things like lithium-ion batteries which are used in cars and things come here. Oil and coal are somewhere up here. Nuclear technologies, fusion and fission, are right up here. So we've got an awful lot of energy in a small amount of fuel, which is why they're particularly useful. Also, they're very clean forms of energy. Certainly fusion is a very clean form of energy without carbon. We don't burn carbon in the same way. So what happens in the fusion reaction? Well, what you take is some hydrogen. Now it's special hydrogen because hydrogen atoms usually have one proton in their nucleus. The center of the atom, the nucleus, has one proton, which is this positive thing here. But in the fusion reaction, we're going to use heavy hydrogen called deuterium, which has a proton and a neutron. Okay, and neutron is neutrally charged particle. We're also going to react it with another kind of hydrogen, which has one proton, but two neutrons. So it's even heavier hydrogen. And if you squish that up and you heat it up enough and you get it close enough together, then you can get it to fuse and join together to make one big nucleus. And when it does it, it kicks out helium, which has two protons and two neutrons. It's a normal helium nucleus, and an extra neutron. And this neutron's got 14 mega electron volts of energy, which I'm guessing won't mean very much to a lot of you, but that equates to a speed of about 52,000 kilometers per second, which is about a sixth of the speed of light. So that neutron's got an awful lot of energy. It's moving very fast. Problem is, it's very difficult to achieve this. In the sun, this happens because you've got a lot of gravity that helps you achieve the conditions you need. But we need to do it on Earth in a machine, and we need to get 150 million degrees in this machine. So you'd think that's not terribly compatible with superconductors, which need low temperatures. But that's what we need in the plasma, and we need a lot of pressure to confine it in one place. And it's that confining the plasma into one place that we need to use superconductors for. So this is a sort of schematic of what a fusion reactor might look like. The purple thing here is the plasma. That's where the reaction's happening. And to keep it in one place in space, you can't have any materials. It's far too hot. All the materials would vaporize. So we use magnetic fields, and they're created. These D-shaped coils are the ones that basically confine the plasma. The amount of fusion power that you can get out of a device like this scales with the magnetic field to the power 4. So that means that if we double the magnetic field that we've got, we will multiply the fusion power by 16 times. So in order to get these things to work commercially, to make lots of energy, more energy than we get out, than we put in, we need big magnetic fields. And that's where we use superconductors. It's only really commercially viable with superconductors. Only get net energy coming out of these reactions if we use superconductors that don't guzzle all that energy just generating the magnetic field. So this is the large fusion reactor that's being built in the south of France, ITER. It's been sort of conceived from the late 80s, actually, and it's taken a long time to get to this point. It's being constructed now. Here are some of the coils. This is one of those TF coils, one of those D-shaped coils. So you can see the scale of it. And this is it being delivered to CERN, to ITER, to the place where it's being built in the south of France. So they're huge magnets. And the problem with this kind of, the whole fusion story is that it all takes a long time. So it was 1988 or something that this started being built. JET was a bit earlier than that in the 70s. That's the big tokamak in the south of Oxford. And everything's taking a long time. So there's some new technologies that have come out quite recently, which are much more compact. So the geometry of the device is different. And there are places like Tokamak Energy, which is a company, private company just south of Oxford, that are making this kind of compact device, Tokamak. There's also Commonwealth Fusion, which is run with sort of MIT is involved in that in the States. And they're also building really what's quite a similar machine. And these are going to need magnetic fields of about 20 Tesla to get them to work. Now that again probably doesn't mean very much. This again is a very famous graph that lots of people who work on superconductors have seen lots of times before. It tells you how much current density you can get through a material as a function of how much magnetic field it's sitting in. So if we look at niobium titanium, which is our favorite superconductor because it's cheap and easy to use, it sits down here, which means it's fine so long as we're not at very high magnetic fields. Now, an MRI machine uses niobium titanium and it has a magnetic field of around 3 Tesla. Not all of them, some of them are lower than that, some of them are higher, but conventionally they're around that kind of amount. So niobium titanium is absolutely fine. One of the really strong permanent magnets that you can buy is about 1 Tesla. So that gives you some idea of a Tesla is a very big unit of magnetic field. If we go to the Large Hadron Collider, which is a superconducting machine as well, that needs 9 Tesla. And we do still use niobium titanium because it's much the most easiest superconductor to use, but we have to cool it now. We can't use it at 4 Kelvin, we've got to use it at below 2 Kelvin to get that to work. Okay, we can push its performance out to the right by cooling it a bit more. ITER, the big tokamak that's being built, that needs about 13 Tesla or so. So we can't use niobium titanium, these purple ones. We've got to use the next material, which is niobium-3 tin. But if we look at these compact tokamaks that are being designed now, they need 20, 25 Tesla. We're talking about high temperature superconductors. So the blue and the green lines here are the high temperature superconductors. So they're not only good at working at high temperature, they're also good at working at very high magnetic fields when we cool them down. So there's a couple of choices, but the one that's probably going to be used is this REBCO, it's called, or IBCO. So what's the catch with this material? So we've got materials, they perform really well. We've got applications, liquid nitrogen is quite cheap to use, so we've got lots of power applications that could benefit. We've got this fusion application that needs these really high fields from coated conductors that we can get, these high temperature superconductors. The real problem is that they're very, very expensive. That's one of the main problems at the moment. So if we look, this is one of the graphs that's available on what the cost is of the superconductor. This is a log scale, so it's $1,000 per kiloamp meter, or it was a few years ago. And it's coming down maybe to $100 per kiloamp meter. So we always do it per a certain amount of current and per meter length. And what it needs to do is to get down to somewhere near 10, about this number. And we're quite a long way off that. If we can get down to there, then it will be useful for power applications. In principle, people think we might be able to. This is apparently the practical lower limit for the actual processing of the material. The raw material is somewhere down here. So it's not impossible that we can do it. Okay. And the kind of material, this is an example of that kind of material. So it's nice flexible material, but it costs about $100 for a meter of it. Okay. So why is it so expensive? The problem is in its chemistry, firstly. So this is the unit cell of the superconductor. So if you look on the atomic scale and see how all the atoms are arranged inside the superconductor, it's got lots of different kinds of atoms that are all in different colors here, but they have to be arranged in this particular way. They've got these sort of planes in the structure, and they're separated by other atoms like this. So they're complicated ceramic materials. Here's just a picture of it, just to show you what it looks like in a microscope. If you use a very high power microscope, you can look at where those atoms are, and you can see all of the positions of those. So what's the problem? Why is it so difficult to make? Well, the first problem is that it's a ceramic, and ceramic materials are brittle, which means that making a wire out of them isn't terribly easy to do because they've got the mechanical properties of something a bit like a teacup. Okay. Unfortunately, we can get around that one with using the technology that I'll show you. The other problem is that all those atoms that we've got have got to be in the right place. We've got to have the right amount of them in the right place. And oxygen is a particularly mobile atom, and it comes in and out of the structure really easily. And if we just take one of the oxygens out, say from that place, the critical temperature comes down by several tens of Kelvin, maybe to about 60 Kelvin. Imagine putting that one back in, it's back there where it should be. If we add one in the wrong place, we can lose superconductivity altogether. So these are really sensitive. We've got to get the amount of oxygen just spot on. So what else is there? Why else are they difficult to make? Well, when we make materials, most materials are crystalline. And when we process them, what we do, how they grow, either from the melt or from a reaction that we're doing, is that they start by growing crystals from particular places in the structure. So these are meant to be different crystals that are starting to grow. As they grow, each one grows out like that, and we generate these boundaries between them, where the crystals are not oriented properly with each other. So they've got a misalignment at the boundary. We call them grain boundaries. And here you can see one just shown schematically. They've got a particular angle misorientation, so they're not lined up properly. And the problem with high temperature superconductors like these is that those grain boundaries are enough to block the current flow. So they behave like a dam. They stop the current flowing through the material. So we can't have any of those grain boundaries at all. So most materials are full of them, and we have to work quite hard to get rid of them. What we really need is a multiple kilometre length single crystal that doesn't have any of those grain boundaries in, with all of the atoms in the right place and all arranged exactly how they should be. And that would be ideal. Well, it would be almost ideal. So how do we do it? How do we make that kind of material? Well, we start off with a metal substrate, a bit of ribbon that's metallic. That's this layer here. And we grow layers on top of it of all sorts of different things, different oxide materials mainly, one on top of the other. And then we put the superconductor layer in, very thin, about 1 micrometer, which is about a millionth of a meter, about 1,000th of a millimeter in thickness. And then we put some silver on the top and we coat the whole lot in copper, usually. And that makes us a nice flexible tape. So we've got around the problem of it not being bendy, about not being able to wind it into a magnet or anything like that. But we have other problems to deal with as well. So we've got the grain boundary problem to deal with. And what we do with that, this is just a very rough picture to show you some idea of it. You can take some flexible Lego tape. That's, you can imagine that that's already oriented. So it's a perfect sort of single crystal. You can do that in a metal. You can roll it and you can anneal it and you can get something that's pretty much nicely aligned with all the grains aligned. And then we deposit the layers, those buffer layers in the superconducting layer on top of it. But we do it in a very special way so that it matches the crystal structure. So whatever's underneath it follows that and it grows exactly on top of it with the same crystal arrangement. So if the thing underneath doesn't have any grain boundaries, any of these boundaries in there, then the thing on top doesn't either. And we do that one layer after the other to build up the structure. Now, of course, we don't actually do it like that. What we do is use a machine that's a bit like this. This is the one in our lab. This is a pulsed laser deposition facility. It's got vacuum chambers where we do the deposition. It's got a big laser here. And what you do is you essentially have a solid piece of material of the thing that you want to deposit, and you hit it with a very high power laser and it vaporizes and the atoms get transferred onto the tape that we're trying to grow it on. It's not the only way of doing it, but it's one way. The last thing I want to say on the coated conductors is that we also have to put defects in them. So they don't work if they're perfect. And for those of you who know something about superconductors, you'll know that it's because inside superconductors, they have magnetic field lines, which we call flux lines. And if they move, then they dissipate energy. They create resistance. So we've got to stop them from moving. And that means we put in defects, loads of defects, any kind of defects we like will pretty much work. So I'm going to run out of time, unfortunately. So I'm going to talk for a couple of minutes about neutron damage. So in a fusion reactor, we have a very harsh environment because not only do we have this very high temperature, but very soon, very small distance away, we've got our superconductor, which is now at minus 250 degrees C, so a big temperature gradient. But neutrons, these neutrons move and they get through everything and they knock into our material and they damage it. So what they do is they hit the atoms inside the material and they move everything around like that. And that's bad. So if we look at what happens, this is a simulation of what happens in IPCO when you hit it with a neutron. Everything that you see in a color is an atom that's been moved out of where it should be and is no longer sitting where it should be in the crystal. And you get these sort of regions of damage where the crystal's all been messed up. What it does to the properties is it brings down the critical temperature as we damage it, and it does something interesting to the current. It gets a little bit better first, and then it gets worse. And if we have a little look at what it looks like inside the material, you can see that you get these regions. These are the crystal planes, and you can see you get these regions that are damaged. Okay. And there are lots of things we've been working on to look at what kind of damage we're doing in between those defects. So you can look at the perfect material before you irradiate it. You can look at it after you irradiate it, and actually most of the atoms are still where they should be. So we've been doing a lot of work to try to find out what it is that's going on in the material that's making the properties get worse. So I can't stop without talking about levitation, because what people see with superconductors is the levitating superconductor. So what you've got here is a magnet. Another property of a superconductor is to do with its magnetic properties. And essentially you can get it to fly like this above the magnet. It's not actually very different from normal magnetic repulsion. So if we've got just a normal magnet and we put another magnet facing the other way, it will repel. Okay, in just the same way that we get with the superconductor, but not quite the same way. So with a magnet, unfortunately, what happens is we've got a repulsive force if we put the north poles together, but if we just let go of it and we didn't have the column in the middle, it would just do that. It would turn over and join up, okay? Because the north and south pole likes to join together, so it's not stable. With a superconductor, something slightly different happens. You put a magnet under there, generates a magnetic field, and in the superconductor, we set up currents, electrical currents that go round the edges of the superconductor. It makes it into a magnet, and it makes it into a magnet that points downwards in the opposite direction. And if we turned that superconductor over, the north pole would still be down, even if the superconductor was the other way up. So it's going to be stable. Okay, it's always going to be repulsive. It's never going to attract. There's much more stable kind of levitation with superconductors. And it's even better than that. So now we've got a magnetic track down the bottom here, and we're going to float a superconductor on top of it. If we do it in the right way, you can turn the whole thing over and it just stays put. So it's really stable. Okay, it's not even, it's not just repulsion. There's something else that's going on there. And what it is that if we do a special way of cooling it, we start it hot. We've got magnetic field going through the superconductor and we cool it down. We can take out the spacer that's in there. So we're going to cool it down. We'll take out the spacer, and those magnetic field lines get trapped inside in exactly the same position in the superconductor. So when we turn it over, it can neither move up or down. It stays exactly put relative to the magnet, because those flux lines, those field lines are fixed inside the superconductor. They can't move if we've engineered the superconductor right. So what can we use it for? Well, one of the things is energy storage. If we're going back to our energy theme, flywheels. So flywheels are ways of storing mechanical energy to recover later. We've got a nice new demonstration of our windmill, which is essentially like a flywheel. It's got a magnet on the outside and the superconductor's on the inside of that box. And you can see that you can turn it over. You can hopefully see that there's a gap in there so that it's not actually touching. We've got sort of friction, very low friction bearings here because there's no mechanically touching parts. And the other thing you can do is make maglev trains. So this is another nice demonstration we've got. We're filling the train with nitrogen, liquid nitrogen. The superconductors are in the train carriage. Take away the spacer. We've got a magnetic track. And just one push, and that will go round probably about 50 times, just from one push of that. Okay, and you can see in a minute, hopefully, you'll be able to see the gap in between. It's a little bit wobbly, but there's a gap in between there. And we can use this commercially. Well, there are demonstrators. It's not commercial. There's the gap in between. You can see it's just floating. So very low friction. So there's a new demonstrator train for this in China that opened in 2021. I think it started, designed to go at speeds of 385 miles an hour. The world record is actually for a superconducting maglev with a slightly different technology at 375 miles an hour in Japan. But the idea is that we can get very high speed travel and with less energy cost. It is the hope. So I think with that, I come to the end of my whistle-stop tour of what superconductors might be used for, particularly in terms of saving energy or improving our energy situation that we're in at the moment. As you can see, they've got huge applications and lots of things that I haven't talked about today, but a lot of power applications as well. So with that, I will thank you and see if there are any questions.
Sure. So I hope everyone can hear this. We've got a question from online, which I'm going to read out. It's a question from Inigo Howe, and he says, thanks so much for a fantastic talk. You have mentioned a bunch of different applications. we know we don't have much time to solve the climate crisis. Which of these applications do you think is most likely to make an immediate impact? Or in general, what sort of timescales are we looking at in different applications?
It's a really good question, because I think that possibly the ones that are going to be commercially seen most are maybe the wind generators, because companies like GE are building those using conventional superconducting technology, so niobium titanium, which is well established. I think, though, that the high temperature superconducting applications, we need the pull through from something like fusion, which can only be done with high temperature superconductors. And hopefully that will mean that we can increase the amount of these materials, the scale that we're manufacturing the materials at, which will bring down the cost, which will enable us to use them in the rather easier applications, actually, the power applications, which don't need so much performance out of the material, but for which it's just too expensive at the moment.
And is there a question from you? Yeah.
Susie, I believe many groups around the world are aiming at synthesizing materials with the transition temperature of room temperature.
Yeah.
Maybe you would do the same. Do you know whether there is a clear direction where to go in order to reach the goal?
Yeah, so room temperature superconductors are really the holy grail of this, because of course, if we could do all of this without needing the cooling, then everything would be easy. Well, we say that. In fact, we need an niobium titanium, really, that's room temperature, which is a difficult ask. So there are some materials that will superconduct pretty much at room temperature in the recent years. These are the hydrides or superhydrides, which were predicted actually from the only theory of superconductivity that we really have that works, which doesn't explain high temperature superconductors at all, but it does explain these ones. And these are materials that will work at room temperature, but you need pressures of about 150 gigapascals to make them superconduct. So actually, technologically, they're much more difficult than the ones that need low temperatures. And my view on this, I don't know where we'll find room temperature superconductors, because we don't have the theory that explains how they work. So I don't know where we're going to find them. Most of the discoveries have been by chance for the different high temperature superconductors. But I think that more important for applications is what we'd really like, if we could have a niobium titanium at 77 Kelvin, then I think that we'd be really in business. The problem is that the materials that work at 77 Kelvin are so difficult and challenging and expensive to make.
So another question from online, two requests. One is that when we have questions in the audience, could you repeat them so everyone can hear them? They've not been picked up. We have a question from a Bob Barnes, who asks, Super Talk, and says in 1954, St. John Cockcroft opened Zeta, forecasting fusion power in 25 years. In 1995, I heard Sir Chris Smith forecast the first commercial station in 25 years, if funding continued. What's the current forecast for ITER?
It's a good question. ITER's been pushed back and back as well, I think. I think they're looking, Damien might correct me, but I think they're looking 2040, 2035, 2040.
First plasma is going to be this.
You think so? Okay. Okay.
You're talking about tritium.
Okay.
First plasma.
Okay. Yeah. First plasma. They say this decade. Okay.
The current forecast is 2027. We will have to be ready for. Yeah, sorry. The current forecast is 2027. They will have everything ready to be fired. They expect they will have a campaign of 10 years before they get enough information to start building the demo, which should be starting in 2024.
I think the point of these new compact machines is to try to accelerate that timeline that's been very slow. Whether it will work or not, I don't know.
Before you go to the line, any questions?
Leaving aside from the nuclear competition, what's the global collaboration organization would you like to see in order for all of these other technologies to be developed in the future?
So that's a really good question as well, because it's exactly what the community is starting to try to do at the moment, is to get together and look at what needs to be done and what routes we've got to doing that. And Ziad, in fact, is setting up the first meeting is next week for this group of people. So we'll, I think, watch this space. But yes, we need international collaboration. We need collaboration with not just academics. We need all the industrial partners. We need Parliament, politicians, all the governments to be backing it as well. So it's a big job.
So 2 questions about joints that I'm going to combine.
Okay.
So linked, you mentioned you can't join HTS, at least not in the same lead-based way that you can for LTS. Does this limit their use for short-length applications? And then another rather specific question, if lead doesn't work, why not gallium?
Why not?
Gallium.
Okay. So in terms of the first one, we can join HTS, we can join it, and there have been some groups that have managed to make what they call persistent joints. I'm not sure that they get enough current through them whilst they're being persistent yet, but they're very tricky sort of one-off type techniques. But there's a big program in Japan looking at using HTS for NMR magnets, which need this persistence. And so they've been working very hard over the last few years on that. Coater-conductor is really tricky, but we can join it with resistive, with low resistance joints as well. And for most applications, power applications, then that's fine. You don't, and for fusion, you don't need persistent mode joints. So it's for things like NMR and MRI that you need the really properly superconducting joints. And there's lots of work being done on that. Gallium, now Chris will tell me, but I think gallium's got a very low melting point. So it'll probably go liquid quite easily.
Online, Professor Grosvenor is giving a thumbs up.
Yes, I don't know its superconducting properties, but it won't be anywhere near as good as lead bismuth. And the good thing about lead bismuth, lead's a really good superconductor, but lead bismuth is good because it's got a reasonable upper critical field. So it's not just its temperature that it works at, it's that you can get a Tesla through it, which is what they need in MRI magnets, so they don't have to put their joint too far away. So you need it to carry to be superconducting at 4 Kelvin, but also at 1 Tesla field, and that's the tricky part with solder alloys.
Thanks, Susie.
Hi.
Just a question regarding the storage. Obviously, there's a lot of focus on our batteries. So you mentioned SMES.
Yeah.
What are their kind of, why are they not being developed so much? Why is that not a one that you maybe think that should be focused on more compared to batteries? And how could that potentially help that kind of storage?
So I think there are lots of people in the audience that know more about SMES than I do, but I think that its good points are that it could be grid scale. So we're not talking necessarily about your batteries in your cars and things like that, but we're talking about grid scale storage. And I think that's where it will be most viable. But somebody else Bruce probably knows about it. No, you don't know about SMES. There were people talking about SMES earlier on. I'm not an expert in it, but I think that grid scale is where it will work. And there's still a debate about whether LTS or HTS would be more viable there, because you've got to have quite a high magnetic field. So we're talking, for those grid scale, I think we're talking sort of 10 Tesla or so. So yes, it's a tricky application actually from that point of view. Yeah.
So we have lots of questions still coming in online. From Matthew Dye, we have, you mentioned that grain boundaries act as roadblocks for current flow. Is it similar to formation of jogs and kinks? I guess that's a reference to dislocations.
It isn't really the same as jogs and kinks, no. The grain boundaries are essentially regions where there is structural disorder, and that's enough to weaken superconductivity over the easy way to think about it. There's a certain thickness associated with the boundary, which is not superconducting. and then the superconducting current has to tunnel, quantum mechanically tunnel through it. So the thicker that is, the more misoriented the boundary is, the thicker that is, the less current can tunnel through. That's the quick answer.
Okay, we have lots of questions online, but I realise we're going to run out of time. I'm just picking some out. So this is a more blue sky question from Charlotte Gomez. He says, space companies are trying to find interesting materials in asteroids and other celestial bodies. At that temperature, I guess in space, it will be easier to produce superconducting devices and make it work. So do you think this will work in space as a technology? So
one of the places where it's been thought of are for satellite communication. So you can use high temperature superconductors, for example, as filters and things like that for mobile signals. And so the idea of sort of flying those out to space and they're being lighter than the alternative filter technologies is one of them. There have been people who've quite recently been talking about magnetic propulsion systems and whether you could do that with high temperature superconductors. I think it depends where you are in space, where you are with regards to the sun, whether you need cooling.
There's one more online.
One more, go on then. Yeah.
Okay, so a last question from online, looking to the future from a Cory Zhang. What are we expecting for the next generation of superconductors? Well, I would hope that we've got technological materials that are being used commercially in real commercial applications. That's what I would hope for. I think we've got the materials. I don't think necessarily we need to find new materials, although if we suddenly came across a brilliant system that could be made into long lengths of wires by drawing them out and without having to do these complicated processes, then that would be fantastic. But I think we've got materials with the properties we need. It's just about getting them into commercial technologies, scaling them up and getting them cheaper.
With that, thank you very much, Susie, for an excellent.
I won't tell you, I won't bore you with what it's all about now, but it's the idea of the book is that it's an introduction to material science, but through superconductors. So, and it's for a general audience. So it's written for, well, I was thinking about sort of A-level science students when I wrote it, because I think there's a lack of good material science books for that audience, and superconductors capture the imagination of that age group. So that's what I was thinking about when I wrote it, but it's all about the material science. So it introduces lots of material science as well, things like thermodynamics and electromagnetism and a bit of quantum theory and some processing, which are across all of sort of material science.